Okay, so today we're going to finish up chapter 2, which is just this last section, section 7, marginal analysis and in business and economics. So it's kind of just applying the concepts that we've already learned, excuse me, to use all this calc that we've been learning in chapter 2 in some practical applications. All right, so let me show you what I'm talking about here. Okay, so couple things here. The definitions you're going to hear a lot of different definitions. They're similar. They're exactly the same as you've had before. They're just in different contexts, different words we're using here. So let me start with this first one here. Okay, so we've had this before. We've had our total cost is C. Now we're going to talk about the marginal cost. It's going to be the derivative of the cost function. And think about what the derivative is. Remember, it's giving you the slope of the tangent line. That still is going to hold true for every single function, no matter what it stands for. So when you look at a marginal cost, it's essentially showing how much, in this case, the derivative is talking about how much the cost is either rising or dropping as you move to the left, to the right. So every time you add an extra unit, the cost is going to go up, but the marginal cost is basically what the per unit cost will be of this extra piece. Okay, so total revenue, same thing. You take the derivative of it, excuse me, you get the marginal revenue. So at this point, just kind of think of this theme as anytime they're asking for marginal something, whether it's cost, revenue, or profit, they're looking for the derivative. Okay, because that's going to break it down and tell you, again, how fast something is either rising or dropping. Okay, so they say here again, what I was kind of talking about, the instantaneous rate of change. That's what they're talking about for the marginal cost. So they have a application. It's sort of like the actual cost of what's going on. So if you look at this here, what this is breaking down is if you have a given cost, C of X, and then you have an extra piece, another 1. So remember, X is the number of items. So if we were to just find C of X at some point, okay, let's say it's going to be C of 100. What this is going to be is the total cost of making 100 items. As you know from our examples, in the beginning it's very expensive. And I use the example of like if you're printing a custom t-shirt, you have to pay this special artwork cost or screen printing, the making of the screen cost. The initial stuff costs a lot to make the first item. Then if you just produce another shirt, they just use the same stuff and then they don't have to keep charging every time. So the first one costs a lot, but as you get more and more, that's why you see that the cost goes down. It's the same kind of item here, same kind of example here, I'm sorry. In this case, we have 100 items. That C of 100 is what it costs, the total cost for 100 items. So if you get C of 101, it's going to be, again, the total for 101 items. Okay, so the difference of these two is what they're doing right here. That's basically saying, well, C of 100 cost me this much, C of 101 cost me this much. The difference is basically how much that 101st shirt or 101st item ends up costing. So that's what they're talking about here. When you find the next one, when you add 1 to it, that's what's going on with the marginal cost. It's like at this point, from here on, how much will an additional item, additional shirt cost? Even though we might have paid a lot for the first 100, it's just now, if we got one more, what would that be? That's what they're talking about when they say marginal cost. From this point, what will an extra one be? And again, it's the same thing for profit revenue is what's that extra one going to be? So if I sell one more shirt, what's the extra revenue going to be? So R of 100 is going to be a certain total revenue. R of 101 is going to be a total of 101. If you take the difference, that's how much that one extra piece would bring you in revenue. Then, of course, profit is going to be the same idea here. So example of what we're going to be doing. Here's a formula for the total cost of producing X tanks, fuel tanks for cars. And the question is, what's the marginal cost function going to be? So remember, I'm not asking for a specific number. What's the function going to be? So this is the cost function. The marginal cost function is the derivative of that. So we take this function, we take the derivative. Remember the three terms, do each derivative. Derivative of a constant is nothing, so that drops off. Derivative of something times x is just that something, this 90 in this case. And then over here, remember, you take the power, multiply it up front. That gives you a negative 0.1, and you drop the power by 1. This is your marginal cost function. That's all you have to do when they ask anything of a marginal something. Marginal cost, marginal revenue, marginal profit. It just means take the derivative of that original function. Okay, so now they want to find the marginal cost at a level of 500 tanks per week. Well, we take that same formula we just found, this one right here, and we're going to literally find the marginal cost of 500, so you plug in a 500 right here for C, or X, I'm sorry, for X, in the C prime equation, the derivative function. You plug in 500, and we get 40. So what that equates to is, now we interpret this. This is good. The best part that you need to know here out of this beginning lecture is, what does this mean? Well, it means that, excuse me, assuming you have 500 tanks per week, the total production costs are increasing. And that's the key, because your derivative could be a plus or minus answer here. It just means that it's costing you $40 for every extra tank you produce. So basically at 500, the next one's going to be another 40. The next one going to be another 40. Of course, we're just talking right around there at the 500 level. So this is the estimate. What matters here is they're saying the 500 first, the next tank will cost about $40. Now it's an about, because remember we talked about, remember dy and delta y, there's the exact value and there's the estimated value. The derivative is giving you an outlook, an actual guess of what it's going to be. So it's going to be about $40. Now we're going to find the exact cost. So we estimated it's going to be about 40. Now we'll see what the 500 first one is. And remember how we do this. You take the total cost of 501. Now remember, notice this is not the derivative equation. It's the original equation right here. If I plug in 501, that's the total cost of producing 501 tanks. So in that equation, every x becomes a 501, and we see we get this total cost of $42,000. Okay, now we go look at what 500 was right before, the total cost of 500. Again, same formula, not the derivative. We plug in 500. That's telling us the total cost was $42,500. So basically, the difference of these two is what that extra tank costs. And just again, think about it is, here's our total price at 500. We're already here. If we were to say, hey, let's get one more, go run more in the production line, it would be this total price. The difference is, well, how much more did it cost? It costs $39 and where is it? 95 cents. That's the exact cost of what that extra tank would cost. So remember, we estimated by the derivative it would be 40. And notice, go back, the derivative is a much easier way to do this. Okay? We just take the derivative, which is not that hard now that we know our trick, plug in 500, which is a lot easier equation. You look at this derivative, it's a lot better than the original equation because the powers are lower. We have less terms. We plug in the 500 right here, we get a $40 pretty quick. Now we do the actual groundwork of plugging in 501, plugging in 500, subtracting them, and we get the exact value of $39.95. So, like always, the exact value will always take a couple more steps, a little more work. The estimated value is meant to be a lot quicker, kind of a thinking on our feet or running the numbers quickly. We're in a meeting, we want to figure out what's that 40, what's another tank going to cost? We can plug it into the derivative and get a 40 and tell the boss right there, hey, it's $40, about. Then you can go have someone or yourself go figure out the exact and say, okay, the estimate was 40, we're pretty close, we're at $39.95. And back to our same little graph again, like always, this will work for any x. Now we use an x of 500 on the last problem, but anytime you have an x, you can add 1 to it. And if you look at what the derivative is, here's the derivative, this line. This gives you what you project that value is going to be of the derivative. Then you can actually go find the exact value by plugging in the x plus 1, subtract off the x, find the exact one, just like we did right here. Okay, so they say the approximate value of the derivative of x is about the regular function when you add 1 to it minus the regular function where it's just x, and that's what you're going to get. You plug in some number for any of these and you'll get that marginal cost versus the exact cost. Okay, so we talked about this right here. It's going to work the same for revenue and profit, all these. So a lot of these examples in this lecture here, this PowerPoint slide, will be just with cost, but they're going to change it up. It's going to, all these examples work with everything. Okay, so we have a total cost of producing X bicycles. And remember, you plug in X into this function, and that'll tell you the total price of that many bicycles. So if I plug in 100, it's the total cost to make 100 bikes. If I plug in 1,000, it's the total cost of making 1,000. So now they want to go and know the exact cost of producing the 121st bicycle. So remember, if we say marginal, you want derivative, and that's the estimate. If they want exact, you plug in the 121st. You plug in the one before and you see the difference. So that's what we're doing right here. Here's the total cost of producing 121 bicycles. Notice again, no derivative. This is plugged into the original function right here. $25,221.80. That's what it costs to produce a total of 121 bicycles. Well, let's look at before that. What was it going to be if you did 120? It would be $25,120. The only difference here is that you added one more bicycle. So basically, what would that 121st, that extra bicycle, have cost? We subtract them, we find it's about 101. Now remember, my hint to you is, when you see these examples on the homework, on the quizzes, on your future exam, they're going to try to use realistic numbers. So when you're working on these here, now again, we all know bicycles range in how much they cost, but think about it. How much is this? Does this sound right? Excuse me. $101 to make a bike? Yeah, that sounds about average. That sounds about normal. Ask yourself that. If this thing came out to be $20,000, you got to say, wait a minute, are we really making $20,000 bikes? Yes, I know they exist, but the average problem, the ones they're going to use in your textbook and your homeworks here, are going to be realistic examples. So just kind of use that as a check. Use your common sense and ask yourself, does this sound right? Could this actually be the answer to the problem? Okay? So now they want us to find the marginal cost of the 121st bicycle. So when you see marginal, you think, let's get the derivative. And remember, when you're finding marginal cost, you're using the value before. Okay, so that's kind of a weird one. When they want the 121st bicycle, you use the value right before, the 120, because what the idea is that we've done 120 bikes, what's the next one going to cost? And that's giving you the estimation for the next bike. So, go back. Exact cost, you plug in the 121 and the number before to the original equations and you subtract them. To find the marginal cost of a certain item, you plug in the value before, the 120, into the derivative. So we find our derivative right here. It's 150 minus 0.4x to the first. Here we plug in the 120 in place of x, and you get $102. That's your marginal cost, your estimated cost of the next bike. Now go back to the exact that we found. Remember, was this the same formula? Yeah. We got $102. We got the exact value of 101.80. These two numbers should be fairly close. Okay, not always exact, but pretty close. And this is kind of tells you that you did the marginal cost right and you did the exact cost. They're probably both correct problems. Okay, so now we're going to talk about another type of equation here. We have the price-demand equation. Okay, so X is the demand. How many of these items people think they'll be wanting based on a certain price. And you kind of know how this works in general. The more expensive, the higher the price is, it's going to be a less demand. Not everyone wants it when it costs a ton. Just like when it's a very low price, you're going to have a lot of people wanting it. So that's what this equation is made up. Now remember, this varies from problem to problem, example to example. But for this exact one, talking about making a new headphone, they're saying, if you price it at a certain P, we'll tell you the demand is, we're going to expect that this many items will be in demand, wanting to be purchased. So now the first question is, They want you to solve for the price. So if you look at this function right here, it's solved for x, because x is by itself. So whenever you're solving for something, it's what letter is by itself. This is already solved for x. They want us to solve for p. They want us to get the p by itself equal to something. So remember how we do this. They didn't show the example here, but if I take this original equation, your first thing you're going to do on some of your homeworks and some of your quiz problems is solve for p. So what do? We look at our three terms. I want to get the p on one side of the equation. I want everything else on the other side. So I added the 1000p to both sides, so it cancels on the right. We have 1000p on the left. Subtract the x the other side, we move the x over, and then remember, divide everybody by this 1000. And that's how they get the p equals 10 minus x over 1000. Oops, sorry, not x. X over 1000. And that's how this equation emerges right here. That 1 over 1000 is the same as 0.001x. Same exact thing. Okay, so that's what they're doing here. When the first step, they want to solve for the other letter. In this case, they want to solve for the p. That's what they're doing. So now they want us to find the domain. So think about the rules here. You know how domain works. We're going to add a couple extra different pieces to it, but it's the same overall concept. You look at this function right here. What are the restrictions on x? Well, by just looking at that equation, forget the word problem. I know that x can be all real numbers. X can be anything in that equation. But then you have to start to now add an extra dimension of what does x mean? Well, x is the demand here. Okay, so x is the demand. We got to add that to that. So I'll show you exactly how we're going to do this. Find the domain. Okay, so of that function, here's the key. Both of these variables have to be non-negative, which means they can be 0 or they can be positive, but they can't be negative numbers. And just stop and think about what p and x stand for. X is the demand. How many items are going to be wanted by the public? Well, you can have the public wanting 1 item or 10 items or no items, but you can't have them want negative items. So that's why x has to be positive. And same with the price. Price is always going to be a positive number or a 0. It could be a 0. Both these could be zeros, but they cannot be negatives. So that's why we have to clarify. Even though when I see this, I would say x can be all real numbers, we have to clarify because of the word problem as well. No, not all real numbers. It's got to be something greater than or equal to 0. Okay? So the price also has to be greater than or equal to 0. And this is where the third element kind of messes things up. Price has to be greater than or equal to 0. That means this thing right here, what price is equal to, p equals 10 minus 0.001x, that also has to be greater than or equal to 0 because that's what the price is. So we have to first identify that, okay, we have to have our x be greater than or equal to 0. Then we have to go look at the price because the answer has to be greater than or equal to 0. We need to solve for this. So that's what we're doing right here. We take this, and you kind of see I don't like the way they wrote this, so let me get rid of that. I'm going to do this to show you what I'm talking about. This item right here on the right, that has to be greater than or equal to 0. So I'm going to solve for x. All right, so there's two different ways to do this. If I solve for x, I can do this, where I move over the 10, so it becomes a negative 10. Then I divide both sides by negative 0.001. So that gives me an x on the left. That gives me a 10,000. Make sure I get that right. On the right side, but here's the key. If you remember your rules of algebra, whenever you multiply or divide by a negative number, that's what you're doing. So in the course of solving, notice I divided both sides by this negative number. This is something that I'm doing to the equation, the inequality. I chose to divide by negative. So if I'm doing that, the rule is you have to flip that inequality around. So that's how we get x has to be less than 10,000. Now, what they did in the equation was they had this, and it's another way to solve this. I'm not saying one's better or worse. They said let's move over the negative 0.001x. And now, notice I'm dividing by a positive number. So when that's the case, I don't have to flip over the inequality. These two things on the left and the right, they're the same thing. It just means that 10,000 is bigger than x, or x is less than 10,000. Okay, that's the result here. So the permissible values of x, the domain is, we already said it's got to be bigger than 0 or equal to 0, and now we found it's got to be less than or equal to 10,000. So your domain is everything in between 0 and 10,000. So it's going to take a little bit more work on these word problems when you talk about the domain because of these two extra factors. Okay, so like always, pause if you need to review this, and I'll erase things and move on. Okay, so now we have a new headphone, the cost function. So they've found this cost function. C of x equals 7,000 plus 2x. 7,000 is the estimate of fixed costs. And we did this in the very beginning of the semester, remember? That's your startup cost, like the screen cost, the making of a machine, making of a template, a stamp, whatever you want to call it. This is what it costs no matter how many you make. And then this 2x is basically every single item you make costs another $2. So that's where we get the 7,000 plus 2x. So we have our variable and our fixed cost. Now they want to get the marginal cost. Excuse me. We want to find and interpret the marginal cost function. So that means get the derivative. Well, the derivative is just 2. The derivative of 7,000 is nothing. The derivative of 2x is just 2. So what that says is, this is a constant. It means it costs an additional $2 to produce one or more headphones at any level. If you've made 1,000 and you want to make one more, it's going to cost $2. If you've made 5 and you want to make one more, it's going to cost $2. It is a constant function. That's what the derivative is saying, is it's always going to increase by 2. Okay, so sometimes that's easy. Now we get a different one, kind of like the last problem here. We have the price function, and it's p equals 10 minus 0.001x. Number of headphones is x, and they're likely to buy at p dollars per set. Okay, so very important here. As you see all these letters, x, c, r, x, or p, I'm sorry, all the different letters, you have to know what they stand for because they could vary slightly each problem. So know what they're talking about. X is the number of headphones. P is how much it's going to be priced at for each set of headphones. So they want us to find the revenue function of x and find the domain. Okay, so remember what revenue is how much you're going to make for every single item here. So here's an old formula. It costs this much, P. Okay, so think about this. If I sold one item, I make P dollars. So let's just pretend for fun, it's a $10 set, something cheap here. All right. So let's just say, for the sake of argument, P equals 10. That's how much we're selling these for. So if I sell one of them, we make a total of $10. That's our revenue. If I sold 15 of them, then my revenue is going to be 15 times a 10. You guys see that? It doesn't matter how many you make. Whatever you make, that's not your revenue. The P is not your revenue. It's the combination. You multiply the two together. So I'm going to charge P dollars. I'm going to sell X of them. That means my revenue is X times P. That's what we have right there. Okay? So now, let's see what our next slide says. Sorry. Okay, sorry, lost the mouse here. Okay, so there is our revenue function. It's X times P, so you take X, you multiply it by the P that was given right up there, that 10 minus 0.001x, and now we clean up that equation a little bit and we get our revenue function is 10x minus 0.001x. squared. That's the revenue function. Basically what that means is you tell me how many items we sell, I plug it into this equation and I get our total revenue. And same kind of thing, we talked about this earlier. What's the domain of that revenue function? Well, it has to be positive. You can't sell a negative number of items. And it has to be based on the fact that our revenue has to be positive, or our price has to be positive. We know that it's going to be no more than 10,000. Okay, we can't sell more than 10,000 because that'll make our price get too low here. Okay, it can't be below zero. So back to that same revenue function here, they want to find the marginal revenues at each of these prices. So once again, look at this. Here is our revenue. Marginal means take the derivative, and we're going to plug in each of these three values. So here's the equation, the derivative, 10 minus 0.02x, and I just plug in these three numbers respectively in three different times. So at 2,000, when I plug it in here, I get 0.002 times 2,000. That comes out to be essentially -4, and 10 minus 4 is 6. At 5,000, we get R is 0. And at 7,000, we get a -4. Now, what that means is, now notice, let's make sure I clear this up. You can have a derivative be a negative number. You can't have the actual R, the revenue, be a negative number. Okay? So talk about what this means. You'll see a picture in a few minutes. But when we're starting off, remember there's a fixed cost, and then at a certain point, let me go back to that original equation. I know it's not the same one, but like this one. See how there's a fixed cost? We all know how this works is if you only sold one, or you only made one, it costs $7,002. You're not going to sell, you're not going to make up that amount of money on the headphones, so you have to make a lot to essentially cancel off this fixed cost of $7,000. So the more you sell, the better it's going to be. And what happens is we found this revenue function, these derivatives, and it's saying when we only sold 2,000, our revenue is kind of going up and up and up because we're canceling off what's going on here. But at a certain point in our revenue, now it's like, well, we're not making any more money. It's starting to not to be efficient. And then if you make too many, now all of a sudden we're getting a lower revenue. We're making less money. Now, we're not making a negative amount of money. What it means is our amount of money we're making is starting to drop. Our revenue is starting to drop when you make too much. Okay, so now you kind of see the summary here. The revenue is increasing. When you make 2,000 of them, your revenue is going up and up and up. Okay, at 5,000, we're sort of hitting the ceiling. Now we're not really making any more revenue. So what it's saying here is, if you make 2,000, your next one, right here, go back. At this 6,000 mark, okay, this is the revenue function. It's the derivative of the revenue. At 2,000, the next one will give us a revenue of $6. Remember how it is? The derivative is an estimate of what the next one is going to earn you. Well, at this level, it means the next one is going to give me a revenue of 0. So the question you ask yourself is, well, why would I make it when I'm going to get less? My revenue is going to, it's not going to go less. It's going to be the same. Why would I make a 5,000 in first one when it's going to cost? It's not going to give me any more money. And over here, it's the same kind of thing on that last one. If I make a number 7,001, my total revenue is going to drop down by $4. So again, we don't want to make too much because now we're starting to get overextended here. So that's the summary of what I want you to see. And they'll say the same thing here for all three of these. For 2,000, your revenue is increasing for a higher production. At 5,000, it's not changing, and it's actually going to get less revenue when you make more. Okay, and remember that has to also do part of that demand here. The idea is that when you have too many out there, the demand drops. You're not going to have a demand when you have this many of them sitting on the shelves. So we have to know, when do we stop the production? How do we know when to quit making these? Okay, so same kind of thing. We have a revenue, we have a cost, and now here's our little summary of everything. So the cost, remember, is a steady function. It's a line that's going up. The revenue function, it varies. In the beginning, and remember, this is going to be our dollars on the left here. You're not making much money. You're not making much revenue in the very beginning. Right? But at a certain point, now you're starting to do better, and then you start not selling enough. So the cost is constant. It's that line right there. It keeps going up, and you see what people are shooting for. These analysts, what our goal is, we want to be here in the profit. We want to know how many do we make to make a profit, and much more than that, we want to know where do we get our maximum profits. So at the beginning, at this point to the left, we can make them, we can sell them, but we're making a loss, and it's because of those fixed costs, because of that original 7,000. When we hit this magic dot right here, all of a sudden now we're making money. And we're making more and more. And this line, the length of this line is telling us how much profit we're making. And then we start making profit. We're still making profit, but at a certain point right here, now we're not making as much money and our costs are still increasing. Now we're losing money. So this is the sweet spot. This green area is where we want to end up. And we'll take it a step further, like I said, is we want to know not only what is that gap, we want to know where is the best profit. Okay, so we're going to find all of those here. Now they want to find the intersection points because that's what matters. And they call them, see in the graph, those break-even points. That's what we need to find. So you can use a calculator and you can find the intersection points. You can set the equations equal to each other. And that'll work. Excuse me. But let me just show you real quick as we do this with Desmos. Okay, same kind of graphing calculator. We are going to plug in these two. This is our revenue function and our cost function. So we start with R of x. That's going to equal to 10x minus 0.001 x squared. Zoom out a little bit. Okay, you see it's a parabola, and remember, we only want to know it from positives to up to 10,000. That's the only place this applies, like in our graph, up to 10,000. And I know we can change this, so let me show you how we change the domain here. So if I remember correctly, after this function right here, you type it, you hit these curly brackets, which is shift bracket there, and you type in the domain. Like we know it's going to be less than, and you just hit equals, and it makes it less than equals x less than equals 10,000. And you see now your graph is just within the area we care about. I'm going to focus on that right there. Okay, so that's our first function. And now, what the other function was, now I'll type in the second one, the cost function. 7,000 plus 2x. And again, same thing, I will restrict that to the 0 and 10,000. No, 0 is what I meant to say. 0 is less than or equal to x less than or equal to 10,000. Okay, so now you see our two functions, which is pretty much like what they had right here. And what we care about are these break-even points. You see we have 1,000 comma 9,000. What it's saying is, once I produce 1,000 items, I will hit, the two graphs will be equal where they're both going to be at a $9,000 revenue or costs. The revenue and the costs are exactly the same. And then over here at 7,000 and 21,000, when you produce 7,000 items, you'll bring in a revenue of 21,000 and your costs will be 21,000, so they'll be even. Here in the middle, you could pick any point. You can see 5,000 I'm making 20,000, whereas 5,000 only costs me 17,000. So you see the gap right there. You want to find that whole profit area. That's what we care about. Okay? So that's what's happening here when we deal with this, this function, the points we're looking for here. So I believe they were, the same points we had, 1,000, 7,000. And what that means, what matters the most to everybody is make sure that you're producing between 1 and 7,000. Okay, and like I said, we'll get to the specifics soon about what that best price is, but at least you know you better make more than 1,000 to make a profit. Anything less is a loss, and don't make more than 7,000 because any more than that is going to be a loss, because what happens is the demand drops, people buy less, and you're still getting your same costs. So you're going to start losing money there. Okay? So back to what we're talking about here. Okay, so that's our area that we're looking for. And now we want to find the profit function, its domain, and its graph. So remember again, profit's the easy one. Profit is subtract the revenue from the cost from the revenue. So I take r of x minus c of x. So I take this original equation, 10x minus 0.001x squared. That's our revenue. We subtract, which is a parenthesis of the cost right here, and we get this summarized equation. P of x equals this. And notice, before I get to that domain, this is a polynomial. It's a square x and a number. It is going to be a parabola. Because this is a negative first term, it's going to be a downward parabola. Now again, the revenue is going to be, the domain is going to be the same thing. Because you had it between 0 and 10,000, that's going to apply the same thing here. Everything in this homework, in this problem, is going to have the same domain. Your profit function is also going to be between 0 and 10,000. So here's the graph of this, and notice it's a parabola. What this is, and I'll go back to, let me get that Desmos graph up there, so I can just kind of compare the two. Remember, in the beginning, before 1,000, we're losing money. After 1,000, we're making money, but after 7,000, we're losing money. That gets summarized here on this. This is all profit. So before you hit this 1,000, this mark right here, you're losing money, so you're in the negatives. Then after you hit 1,000, now we're starting to make money. We make the most money right here, and we're still making money, but our gap is getting smaller. Then you hit 7,000, now we're losing money again. Now you're losing a lot of money. So again, know the function you're dealing with. This is the profit. This is how much money, the bottom line. How much money you're making, how much money you're losing here. Okay, now what matters is marginal profit. We're going to find the marginal profit. So remember, you have a profit function right here. Marginal always means get your derivative. So we take the derivative of the profit function. We get 0.002x plus 8. That's our marginal profit. So you can plug in all these different values. What it's going to tell you is the profit going up or down at each of these values? Well, at 1,000, our profit is 6. We're going up. Our profit is definitely rising. At 4,000, our profit is 0, means it's not going up nor down. And at 6,000, our profit is dropping. So go back to this function showing it. At 1,000, remember, the marginal profit is the derivative. It's the tangent line. So it's definitely, we're on the up right here. When we hit our 4,000, our profit's not going up nor down. Afterwards, it's dropping and dropping and dropping. That's what these marginals are telling us, is that, hey, when you're making 1,000 of them, your profit is going up and up and up. At 4,000, your profit's not really going up or down. And at 6,000, your profit's dropping. So we probably shouldn't be making that many either, because we're losing, we're still making money. We're still having a profit. But our profit is starting to drop, is what's happening here. Okay, so it kind of summarizes what I just said. And now we start to do things that are going to be important here. What's the cost per unit, the average cost? So they use this line over the top, which means average cost of an item. So to find the average cost, we know how to find the averages. You find out the total. Like when you want to find the average scores of a test, you add up all your test scores and divide by how many, and that tells you your average test score. Your average cost is going to be, you add up the total cost and divide it by x. Now I want to point out something here. There's a mistake. There should not be a line right there. This is supposed to be, make it clear, just plain cost divided by x. Just a little typo in the notes there. So don't worry about that. Just kind of know that it's supposed to be, when you want to find the average cost, you find the total cost divided by the number, like you've always done before. The new symbol is that C with a line over it. Okay, so now the marginal cost, right? What we're going to have next here, the marginal average cost is you're taking a derivative of the thing that you just found. All right? So to clarify right here, oh sorry, yep, you're going to take the derivative of the average cost function. That C with a line over it. So whatever you find the average cost to be, if you can get that as a function, the marginal average is just, again, marginal means take the derivative. So same thing here with the R. Let me get rid of all this now that you see these slides are going to be correct. Your average revenue is going to be the total revenue, Rx, R of X divided by X, and the marginal average revenue is that derivative. The average profit is the total profit divided by X. Your marginal average profit is the derivative of that. Okay, so let's get to some examples so you can see how this works here. The cost of printing X dictionaries is 20,000 plus 10X. Again, your fixed cost is 20,000, and then after that, it's going to be $10 for every single one. So now we want to find the average cost per unit if 1,000 dictionaries are produced. So first off, you get this function right here, which is average cost. You take the total cost divided by X. So they clean this up first. Take this 20,000 plus 10X divided by X. That gives you 20,000 over X plus 10. That's the average cost function. So they want to know, what is the average cost if you do 1,000 dictionaries? Well, plug in 1,000 to this, and we get 20 plus 10, we get $30. It's going to cost an average of $30 per unit if we made 1,000 of these. Okay? So we'll do some more of this. Find the marginal average cost at a production level of 1,000 dictionaries and interpret the results. So kind of make sure you know what we're looking for. When you see marginal average cost, first find the average cost. All right? Well, go back. This is the average cost function right here. This 20,000, right here, apologies. 20,000 over X plus 10. That's our average cost. Now we want to find the marginal. We take that function and we're going to find the derivative. Okay, so they kind of went backwards a second. They left it right here. Sorry. They left it as this. It doesn't matter. This one is going to work. They're both really going to end up right there. So to find the derivative, and what they're not showing is this right here. We make this into 20,000 over X plus 10 over X. This is all for the average cost, by the way. I'm not doing a derivative yet. Okay, so now I get 20,000 X to the negative 1 plus 10. Now I can find the derivative. I had to get it into the polynomial form. So take the negative, we get negative 20,000 X to the negative 2. The 10 cancels off when I do the derivative. And that's how they get that right there. So I just want to make it clear, how did they jump to that level? They broke it down, they took the derivative, and they got this answer. So again, pause right here if you need to see how this works, and then unpause and we'll resume. Excuse me. So now we get this. They want to find the marginal average cost at 1,000. So we found the marginal average cost formula right here, negative 20,000 over X. Now you plug in the 1,000 and you get a negative 0.02. Okay, so what they're saying is your average cost, your marginal average cost is expected to go down about 2 cents every time you go up there. All right, so now use the previous results to find the average cost per dictionary if 1,001 dictionaries are produced. Well, remember how that works. The average cost for 1,000 dictionaries is $30, what we did first. The marginal average cost is negative 2 cents, so that's going to estimate that you're going to get a $29.98. What it's going to be, because it's every one after is going to be 2 cents less. So that's how we get down to this $29.98. Okay, so they give a little summary here of this caution. Be careful what you do. You have to get the derivative. Okay, so first you get the average cost, then you find the derivative. Don't do the derivative, then the average cost, because if you do them backwards, it will not be the same results. Okay, instantaneous rate of change and the approximating the exact cost of producing X plus 1, the next item. All right. Excuse me. So let me go with some examples here. So back in our course here, we're at the next week's homework. I think we're on homework number 6. Way down here, and for most of you, these aren't showing because we're past them or we've completed them. My assignments show them all here because I haven't done them and submitted them. So homework number 6, we have 2.7 and 3.1. So we're starting with the 2.7 stuff today, and then the next video will give you the 3.1 assignments. So let's kind of just talk about these to make sure we're all on the same page with these. Let's get that calculator out because I'm sure we're going to need that in a minute. Okay. All right, so they want us to find the marginal cost function. Remember, here's the cost function. Marginal is, let's find the derivative of that. And I can do this in my head. You can do this in your head, but I'll just show it just in case. We're taking that cost function right there. We're going to take the derivative of that. So we take c prime of x, and we get the derivative of 174 is nothing. The derivative of 1.5x is just 1.5. So that should be our answer. That's all it takes. You know, on some of these, there isn't a whole lot of work. It's, you know, kind of quick on the first few examples. So don't think twice of that. Don't think there's a problem, I should say. All right, let's look at number 7. Kind of follow the same pattern I always try to do here. Now we have the marginal, or find the marginal profit function if the cost and revenue are given by this. So remember, to find the marginal profit function, you have to take the derivative of the profit function. Well, they didn't give us the profit function yet, so we have to do that. Remember, profit is always going to be the revenue function minus the cost function. Okay, so my profit function is going to be the revenue, which is 2x minus 0.01x squared. So that's revenue. Subtract the cost function, the 215 plus 0.3x. Okay, so when I remove the parentheses and add things up, and again, you don't need to do this middle step. I'm just doing an extra step so that everyone understands how we're getting these values. And to clean it up, you always want to try to put the highest powered term first. This is going to be plus 1.7x minus 215. And you see the 1.7 is because I added up the 2x and the negative 0.3x. And that should be my profit function. All right. So I just plug it in and notice, oh, sorry. I'm glad I didn't put this in here. This is why I always write the stuff. Notice, I got to get p prime of x. I've just found the profit. So before I start to write in here, I can't do that yet. I haven't found my derivative. So that's one reason why it's good to have everything labeled, because I see p prime x is not equal p of x. Don't put that in there. Now I'm going to find the derivative. And I get a negative 0.02x plus a 1.7. And the minus 215 disappears. That's my marginal profit function. Negative 0.02x plus 1.7, and there's our answer. Okay, again, keep pausing if you need to look at this over and see it. If not, we'll move on to the next one. Unpause and we'll move on. And let's see what number 11 is all about. Okay, on this one, find the total cost in producing X food processors if C of X is all this. Okay, so first, find the exact cost of producing the 21st food processor. So remember what we're doing here. When they want to find the exact one, we're not talking about that. We want to see what is C of 21. So I plug that into my original equation. I get C of 21 is 2200 plus 20 times 21 minus 0.2 times 21 squared. Okay, so clean this up and do not feel you have to do all this work at once. Take your time, plug this into a calculator. In this case, where's my calculator? Right over here. So I'm going to take the 21 squared, 441, times that by 0.2. So I get a negative 88.2. So keep going on this one. We're going to add the 420. We're going to add the 2200. And we get 27082. Now let's make sure we interpret these results fine. What this means is the total cost of 21, what are they, processors, items, I'll just say items here, is $2,708.20. That's the total cost of making that many. So it's not making one, it's making 21 of those items cost that much. Okay, now what I have to do is, same thing, I want to figure out, well, what was it when we only made 20 of them? So I go back to that original equation and plug in 20. Like I said, don't feel you need to do this all in one step on your calculator. Write some steps out just so you can see what's going on here. So like before, I'm going to take the 20 squared, which is 400, times that by 0.02, and we get 8. Oh, sorry, not 0.02. I knew that didn't seem right. I messed up on the equation. Let me try this one more time. It's 0.2. Okay, so back to our 400 times 0.2. Sounds better, 80. So the total cost of 20 is going to be 2625.20, I believe. Don't feel bad using your calculator, because you need to get it correct. That's more important than doing these in your head right now. Okay, so remember, this is the total cost of producing 20 of them. So this is how much your bill was right here when you made 20. If you were to build another one, it would be up to here, so we subtract these two. 2708.20, subtract off the 2520, and we get 188. I hope that's right. Yeah, 188.20. So what that's saying is, this is the production cost when you made 20. Now it went up to here. How much more did it change? It changed by $188.20. That's the exact extra cost of what that other next process. Oops, did I get it wrong here? What did I miss? I got to check my work now. What it should have been the exact cost of producing the 21st food processor. Let me just check the work here real quick. See if you can tell what I'm doing wrong as I check this. Okay, we can see what it is. I see my mistake now. Go back over here on the 21. 2200 plus 420 minus 88.20. And this is kind of a lesson learned from me here. Why you don't want to try to do this in your head. It's more important to get it right. Add these up in a calculator. We get 2620 minus the 88.2. And this is what we should have. So I think I added when I should have subtracted right here. This is supposed to be $25.31.80. So that's the one that we're going to subtract. That's how much it costs to make 21 of these. 25 of them cost that. So I'm going to take that answer, subtract the 25.20, and we get $11.80, which now I start to look at it. I got done telling you, and I didn't even follow my own advice here. These are supposed to be real life examples. Food processors shouldn't be $188, the cost of them. They should be a lot less. And specifically what did I say that was? $11.80. And now we have it. So big mistake right here. And you see, it wasn't a huge thing. It was one little error on my calculator. I hit a plus instead of a minus right here. That changed this total, which of course changed the difference, and that's why we got the answer wrong. All right, so now that we have that, now they want you to use the marginal cost to approximate, and remember how that works. To get the to approximate with the marginal, we need to say, okay, marginal means derivative of the cost function. So here's my cost function right here. 2200 plus 20x minus 0.2x squared. So the derivative of the cost function will give you the marginal cost function right here. That becomes nothing. We have a 20 minus 0.4x. So they want to know what's the approximate cost of producing the 21st. Remember how that works. When you use the marginal, the derivative, you're going to use the 20th. You go one down. So I plug in 20 right here. And we get C prime of 20 equals 20 minus 8. And that gives us 12. So that is our estimated, our approximate cost is going to be $12. And you know you're in good shape because, okay, if this was the actual cost was $11.80, this is pretty close. That means our estimate was good. Okay? So let's look at number 15 here. Similar type problem, a little more. Price dollars and the demand for a particular clock radio is this equation right here. In part A, express the price in terms of X. So this is one of these where we take that equation and we're going to solve for X. Sorry, solve for P. So I take that and I'm going to solve for P. So move the P over here. Let's move the X over there and divide everybody by 50. And we get 100 minus X over 50. So that is our P function. 100 minus X, 100 minus X over 50. And we're good on that. Now they want to know what's the domain. So remember the rule here. The domain, the X is fine, so it can be all real numbers, but X has to be greater than 0. So it's not going to be this all real numbers thing. That looks okay. It can't be this one because this could give you numbers that are way down below 0. The first part is yes, X has to be greater than 0, but remember, that has to be greater than or equal to 0. So we take this answer, since that's what's equal to P, and we also have to set this greater than or equal to 0. Now, it doesn't matter how you do this. I did it where I left the X on one side. I did it both ways last time, but let's move this over. Get 5,000 is greater than or equal to X, which means X has got to be less than or equal to 5,000, and it has to be greater than or equal to 0. That's that first answer right here. Okay? Got to get the two pieces. It has to be number 1 greater than 0, and then you have to figure out what the function you just found has also got to be greater than 0. Okay, and part C, find the revenue function. So remember the rule. Without even looking at the problem, I kind of remember, oh yeah, revenue function is supposed to be cost. No, it's not cost. It's got to be the price, but it's not just the price. Okay, remember, what's the price? That's just telling you how much each item is sold for. My revenue is how many items am I selling? Multiply that by P. So the revenue function is going to be X times what we just found for P, which I have it right here, so I can look at that. It's that 100 minus X over 50. And of course, you have to clean this up a little bit. Notice every time I'm writing that R of X. Your slideshow doesn't do that. It doesn't always do that in the online explanation. I do that because I want to make sure we all know exactly what we're dealing with. Because when I find the derivative, it's going to be something else. When I find the profit, it's going to be something else. I have to make sure I know where I am on every single line. So there's my revenue function. Right? So we have 100x minus x squared over 50. I hope I did that right. Yep, we're good there. And last, they want you to interpret that R prime of 3,100 equals negative $24. So, oh, I'm sorry, part C. We're still on part B, am I right? Yeah, I'm sorry, we're still on part B. Apologies. We want to find the domain of this. Well, it's the same rule where you have to make sure x is greater than 0. And now we have to look and see, well, what's that mean for the revenue function? All right. So the revenue function also should be greater than 0. Is that a guarantee or is that not? That's the big question at hand. Okay. So, excuse me. If I was to try to do this, I don't need to, because remember, if I look at that graph before, when we talk about revenue, you could have revenue here that's down here in the negatives because it means you're losing money. Okay, a negative revenue means a loss. So it is not true that revenue has to be greater than 0. What it reverts back to is what you had earlier in the function. The domain that we had to begin with is you still have to have, domain of R of X. Sorry, where am I at here? Oh yeah, X is the number of items that we're selling here. So we have to sell a positive. So it's going to be either this one or this one or this one right here. We just have to look and make sure what we're dealing with is going to be a positive in terms of where the price was originally, that first function right here. That same one. So if you remember, it was that right there, less than or equal to 5,000. Was that what we had? That one right there. The domain of the profit should follow to the revenue. And you see it's the exact same thing right here. We get that D, it's the same thing. So kind of a tricky one. Just remember, whatever it is for the profit, that has to be a certain set number. It's going to translate right over to the revenue. The revenue does not have to be greater than 0. So whatever you found as the domain for the profit is the same thing for the revenue right here. Okay, so now the marginal revenue productions level at 2,900 clock radios is, well, take this revenue function. All right, so let me go rewrite that one more time. The revenue function, which we just found, is 100x minus x squared over 50. The marginal revenue, marginal means you need to be finding a derivative here. Okay, so the derivative is just plain 100 minus 2 over 50x. So I'll clean that up a little bit and say the marginal revenue is 100 minus 1 over 50x. So now we're going to plug in the 2,900 into that. We want to find R prime of 2,900. So that's going to be 100 over, minus 1/50th of 2,900. And that's where we got to get your calculator out again and make sure that you're doing all these right. Because it's no point in doing this and then going right to a calculator, and skipping your calculator and you get it all wrong. Okay, it's most important, just get that number right. Okay, give me a second. I'll get the calculator going here. All right, so I'm going to take 2,900. Let's clear it out just to make sure. 2,900 divided by, sorry, do that again. 2,900 divided by 50 gives me 58. I'm subtracting that from 100. And I get a 42. So that's the marginal revenue at that spot. And what did I mess up on? Did I plug in the wrong number? Let's try it again here. All right, let's make sure. We got our revenue, 100x minus x squared over 50. The derivative is 100 minus 2 over 50. Oh, there's my mistake right there. I really don't know how I messed that one up so bad. Let's fix this. Okay. Good news is you can just fast forward on the video next time if you have to watch this twice. But let me clean this whole thing up here. Okay, got to get the derivative correct. So 2 over 50. I think I said it, I just didn't write the right thing, so that messed up my next step. That should be 1 over 25x. Okay, so when I plug this in, it's 1 over 25 times 2900. All right, so we had the wrong one, and that's what, of course, it's always going to be a chain reaction here. You mess up one, everything follows is going to be bad. So we get 116. We're going to subtract that from 100, which you can do in your head. We get a negative 16. So does this seem right? Can you get a negative 16 marginal revenue? We'll find out. And it is. What that's saying is at the 31, sorry, where are we at here? At the 2900 level, your revenue, your marginal revenue, but your revenue in general is starting to drop. It doesn't mean you're losing money yet. It just means the amount of money you're taking in is starting to go down. Okay? So which of the following statements is not true, not a correct interpretation, sorry, of R prime of 3100 is negative 24. So forget the right or wrong yet. Let me just talk about this in general. What this means is at the level of 3100 clock radios, our revenue is starting to drop by $24, or for what we have here. We're losing $24 each time we produce a new one off of our total. So that's what the first one says. That looks good. There will be no revenue since it's negative. That doesn't mean it's true. You can still be making money, but your total revenue is starting to drop. Sorry. And then, of course, remember, when you plug into a derivative, it's talking about the next clock radio is going to drop our revenue by that much. So A and C are correct. It looks like B is our wrong one. And there we have it. Okay, now at this point here, I'm gonna stop on the homework because you don't have a lot of homework in this section. It's kind of a nice week, and it fits because we're kind of short with a holiday week here. So let me show you where we are. Okay, so what we've done here, the first few, if they pop up, let's go back to our homework number 6, where we are right now. You see, we've done the first 4. That's it for section 2.7. It's not a huge section. It's like, the first 45%. Then we'll start chapter 3.1 on the next video, and you'll see the rest of these. But fairly short homework, and it's not that much work on these, so you should be able to at least do the first almost half of these. Okay, so look out for the next video. You'll see that soon, and don't forget to do your quiz, which is actually due on Tuesday night because of the holiday on Monday. So you actually have another day. Short week this week, so homework assignment's not as bad. Okay, that's it. We'll see you next time.